Imagine a world where the next Cold War isn't fought with missiles, but with qubits. What if the very fabric of global power, alliances, economies, even defense, is being rewritten right now, not by politicians, but by quantum engineers? This isn't science fiction. It's the quantum race unfolding today. Across continents, nations are racing to build quantum computers that can achieve what's called quantum supremacy. This would allow them to crack encryption, simulate complex systems instantly, and leap ahead in defense and innovation. In the United States, federal initiatives and private giants are pushing research with billions. In China, massive state-led programs are designed to secure dominance. Europe, too, is determined to stake its claim. But this is more than scientific progress. It's a geopolitical contest for influence. Which nations will lead? And how will quantum technology reshape our world? Stay with us as we unpack the silent battle over qubits. Imagine a world where the next Cold War isn't fought with missiles, but with qubits. What if the very fabric of global power, alliances, economies, even defense, is being rewritten right now, not by politicians, but by quantum engineers? This isn't science fiction. It's the quantum race unfolding today. Across continents, governments and corporations are racing to build the first quantum computers that can outperform traditional computers in real-world tasks. This milestone, known as quantum advantage, could allow nations to crack encryption, simulate complex systems instantly, and leap ahead in defense and economic innovation. But what exactly is a qubit, and why does it hold the key to this new era of power? Unlike a classical bit, which can only be a 0 or a 1, a qubit can exist in both states at once. This property, called superposition, allows quantum computers to process an immense amount of information simultaneously. Think of it like this. A classical computer would try every key on a keychain one by one to open a lock. A quantum computer could essentially try all the keys at the same time. This exponential increase in processing power is what makes quantum computing a game changer. The implications are staggering. Let's start with national security. Much of our modern world runs on encryption. From your bank transactions to government secrets, everything is protected by complex mathematical problems that are currently impossible for classical computers to solve in a reasonable time frame. But for a powerful quantum computer, these encryption methods could be as easy to break as a child's piggy bank. The first nation to develop a large-scale, fault-tolerant quantum computer could potentially unlock the secrets of its adversaries, rendering all current digital security obsolete. It's a scenario that has intelligence agencies and military planners around the world losing sleep. This brings us to the front lines of this quantum Cold War. In one corner, we have the United States. With a combination of massive federal funding through initiatives like the National Quantum Initiative Act and the powerhouse R&D departments of tech giants like Google, IBM, and Microsoft, the U.S. has been a traditional leader in technological innovation. These companies are not just publishing papers. They're building real, albeit still experimental, quantum processors. They're creating entire ecosystems of software and hardware, attracting the brightest minds from around the globe, and fostering a competitive environment that accelerates progress. The U.S. strategy is a mix of public-private partnership, aiming to maintain its technological edge through a decentralized, innovation-driven approach. In the other corner stands China, which has made quantum technology a cornerstone of its national strategy. Unlike the U.S. model, China's approach is state-driven and highly centralized. The government has poured tens of billions of dollars into massive national laboratories and programs with the explicit goal of achieving dominance in quantum communication and computing. Chinese researchers have made remarkable strides, particularly in the field of quantum communication. They launched the world's first quantum satellite, Mischius, which successfully demonstrated hack-proof communication over vast distances. This technology could one day create an unbreachable communication network for its military and government, a significant strategic advantage. On the computing front, Chinese scientists have also developed impressive quantum processors, claiming to have reached quantum advantage on specific tasks, directly challenging the progress made by their American counterparts. And it's not just a two-horse race. The European Union, not wanting to be left behind, is also a major player. Through ambitious programs like the Quantum Flagship, the EU is investing billions of euros to coordinate research efforts across its member states. Countries like Germany and France are also launching their own national initiatives, building quantum innovation hubs and funding both academic research and startups. Europe's strength lies in its deep-rooted scientific institutions and its collaborative approach. The goal is not just to compete, but to ensure technological sovereignty, so it isn't reliant on either the US, or China for this critical future technology. Other nations, like the UK, Canada, and Japan, are also investing heavily, turning this into a truly global competition. The battle isn't just happening in labs. It's also a fight for talent and resources. Quantum physicists and engineers are in incredibly high demand, and countries are competing to attract and retain these experts. The supply chain for building quantum computers is also a new geopolitical choke point. Specialized materials, cryogenic equipment, and precision lasers are all essential components, and control over these resources could become a source of leverage. We could see trade restrictions and export controls on quantum-related technologies become the new frontline of economic statecraft, similar to what's happening with advanced semiconductors today. Beyond cracking codes, the economic prize is immense. Quantum computers promise to revolutionize industries. In medicine, they could simulate molecular interactions to design new drugs and therapies in a fraction of the time it takes today. For climate change, they could help develop new materials for more efficient batteries or create catalysts to capture carbon from the atmosphere. In finance, they could optimize investment strategies and model economic risks with unprecedented accuracy. The nation that leads in quantum computing will likely dominate the high-tech economy of the 21st century, creating trillions of dollars in economic value. This economic dominance, in turn, translates directly into global influence and power. However, the road ahead is filled with immense scientific and engineering challenges. Building a stable, large-scale quantum computer is incredibly difficult. Qubits are fragile and easily disturbed by their environment, a phenomenon known as decoherence. Keeping them stable requires extreme cold, near absolute zero, and shielding from any external noise. We are still in the very early days of this technology, what some call the noisy intermediate-scale quantum, or NGSQ era. Today's quantum computers have a few hundred, or at most a few thousand, qubits, and they are prone to errors. To break current encryption standards, we would need a machine with millions of stable, interconnected qubits, something that might still be decades away. But the race is not just about the final destination. It's about the journey. Even the intermediate steps and smaller-scale quantum devices can provide significant advantages. Quantum sensors, for example, could be used for incredibly precise navigation without relying on GPS, a huge advantage for submarines or military operations in satellite-denied environments. Quantum simulation, even on imperfect machines, can already solve problems in materials science that are beyond the reach of classical supercomputers. So who is winning? It's hard to say. The U.S. currently has an edge in private sector innovation and software development. China is a leader in quantum communication and is rapidly closing the gap in computing through its massive state-led investment. Europe is a strong contender with its collaborative research base. The truth is, the lead changes hands constantly as new breakthroughs are announced. This race is a marathon, not a sprint. The quantum revolution is coming. It's a silent battle being fought in laboratories and boardrooms, but its outcome will shape the world for generations. It will redefine our security, our economies, and the very balance of global power. Which nations will lead? Which will fall behind? And how will this technology reshape the world order? The future is being written in the strange and powerful language of qubits. The quantum Cold War has already begun, and the world may never be the same. Thanks for watching, and if you want to stay ahead of the curve on the technologies shaping our future, make sure to subscribe and hit that notification bell.